I have to be honest that this talk has just absolutely scared the living dickens out of me, and as no talk in a long, long time, because I wasn't quite sure what right I have to even be here talking about this. And I say that in all true modesty. I really mean it. I'm not sure anyone has that right to stand up and tell people about how they should teach. But what I can do is give you the benefit of my experience, and you can take with it and do with it whatever you please. And so we'll try and do that. And the other thing I want to do is show you a product of something that I've thought about for many, many years and never really had the energy and to try, but fortunately one of my colleagues at Stanford, Bud Homsey, did, and I'd like to show you. It deals a lot with images, which is what we're going to talk about today, and I'd like to show you a little bit about how all these different media and images can be blended by the use of technology and how it can be used in teaching. So that's what I like to do today. All right. Whoops. Yeah, technology is failing. All right. So, let's start out. Now, I have to thank Fred for actually telling me what I was going to talk about, because after he said, "What's your title going to be?" and I ignored him, and I ignored him, and I ignored him, and I couldn't think of a title, and then I thought, we'll try and say something smart, and I tried to say something smart, and that's what came out, and then I thought, well, what does it mean? And then Fred told me what it meant. He sent me back, he said, "This is what you mean, right?" And this is what he wrote. And it's exactly right. He pointed out to me what I should be talking about. And that is something that I think is apparent to all of us, that we have many different learning styles. And sometimes images speak to students in ways that equations or words do not. And I think that's very true. Many years ago, we had a retreat as a department, and one of the exercises we went through, which was greeted with utmost skepticism at the beginning, was, how do people learn? And everyone, oh God, do we have to do this? Yes, we have to do it. And so we filled out this little questionnaire, and everybody started getting into it, and then there was a way of scoring it, and then plotting it up, and I can't remember what this, Robin probably knows what this is about. And then afterwards you analyze it, and you get these little quadrilateral shapes, and depending on how long this axis is relative to this one, it tells you what kind of learner you are. Are you a type 1, a type 2, a type 3, a type 4? And everybody by this time was really into it, you know. Are you a type, who's type 1 around here, and who's type 2? Well, type 1 are the kind of people that, you know, you give them a homework and they want, here's the problem, here's the data, you know, get the equation, plug it in, solve it, out it comes. And then you get the type 4 people, you know, who want very open-ended problems and really do well with that, you know. The kind of question where they would spend many hours trying to debate exactly what the question meant before they were even, you know, answering it. And I think you have to be aware of that when you teach, that there are people who learn in different ways and have different learning styles, and I think you have to try, whenever you're teaching, to acknowledge that and to work to that. Now, in teaching fluid mechanics, fortunately, it is something that is image-rich. Pictures and graphic representations of data are obvious when teaching fluid mechanics. But the one that's not as obvious, the images that are not as obvious, are the ones that come through anecdotes, or war stories, as I like to tell them, because these are things that evoke clear mental images, but often are not used. And so this software, or this piece of software that I want to show you at the end, is an attempt to take the traditional imagery that you can use in teaching fluid mechanics, which are the pictures and the graphic representations, but blend in the non-traditional, which are the anecdotes and the stories. And when you're thinking about fluid mechanics, you say, well, you know, wow, there's fluid mechanics you're talking about here. But I would like to show you how perhaps that does reinforce or enrich the subject or body of knowledge. So we'll talk about that a little bit. So many of you are probably going to embark on careers as professors and teachers, and you know that in the beginning you're going to be expected to do many things. and you're going to be wearing many hats. I mean, this morning, and it doesn't get any better. This morning I was doing a lot of things, and I was trying to get my head into this talk, and let me tell you, every time I try to get my head into this talk, another one of these caps showed up, and I had to go do this, that, and the other. So you're going to be dealing with this problem all the time. You've got lots of challenges to meet as a young, professor. You're going to go out there, perhaps like Don Quixote, you're going to have to choose which windmills you're going to start tilting at. And you're terrified. I mean, I was absolutely terrified. I remember the first time I stood up and gave a talk, and at that time my colleague Bob Street, I was his PhD student, and he felt it was appropriate to critique and give you feedback on how you did. And I just didn't even realize it, but he told me, you tended to put your hand on your butt a lot. So I was so terrified, I didn't even know it. So I got my hands in my pockets because you never lose that terror, let me tell you. In many ways, I'm terrified right now. Okay, let me give you a little contextual background. I come from South Africa, as was indicated. I went to the University of Witwatersrand, and a lot of the faculty look exactly like that gent on the right. I mean, I went to lectures, folks, where people actually lectured in academic gowns. Either that or their lab coats were really dirty. But this was a stiffness, sort of British system where students were meant to be seen but not to be heard, and here's the knowledge, you take it and take the exam, and in this, that, and the other. There was very little interaction. That stern-looking person there in many ways symbolizes sort of the experience that I had as an undergraduate. Then I come to Stanford. Oh my God. What a mind blower. I mean, I think the second day I'm here, I go to a departmental meeting, and there's the chair of the Department of Civil Engineering, as it was known there, standing up on a chair. He didn't have a tie on. He had an open neck shirt, which was a big change already. And under this open neck shirt, he had beads, for God's sake. Turns out they weren't beads, they were puka shells. But that's all right. And I'm thinking, what is this place, It was a completely different atmosphere. Classes had teaching assistants and course assistants, something that was never, ever the case in my experience as an undergraduate. There were office hours where students were encouraged to attend. Students were encouraged to have an interaction with faculty during a lecture. It was a completely different experience. And so suddenly this image that I had of professor completely turned around after my coming to Stanford. Now, for many of you, that's probably not the case because you went to universities where they were very similar to Stanford. But for me, the contrast was extremely stark, and it had a very big influence on me because I had absolutely no interest, I can tell you, when I came to Stanford in even thinking about teaching as a career. But when I came here and I saw this, and I saw this whole interaction, this different image of what academia is about, it completely changed my mind and opened it to the possibility. And I actually found that even though I was still terrified, that I was going to enjoy it. So what is this Cheerio all about? In starting my career and in thinking about how I teach and what makes a good course, I've tried to write down what I think is important to me when I'm developing a course or when I'm teaching. What are the things that I think are essential to putting together a course, and any course, not just one in fluid mechanics. And so I go by the acronym Cheerio, which works pretty well. And some of them are very obvious. Challenge. I think it's really important that students feel challenged in a course. I must admit, I don't do as good a job in that regard as I should. I probably don't challenge students as much as I should in my courses. Many people here have taken courses from me, and they'll probably say, yeah, that's true. They've had professors who challenge them a whole lot more. But I think that's an important element. I think you can challenge people and encourage them to work extremely hard without making the course feel overly burdensome. And I think that's something that you shouldn't shy away from. It's an important element. But if you want people to rise to the challenge, and if you want them to really pay attention and participate in the course to the degree that you expect, even though, of course, you're teaching a 3 or 4 unit course that is maybe 20% of a person's time or effort during any academic quarter, you, of course, demand 100% of their time. You think it's the only course that's relevant. If you expect that, then you should be prepared to put the same kind of effort in. And energy is incredibly important. So if you walk into a class, giving the impression that you're there just because you have to be and you're not really interested in it, don't expect any miracles and don't expect people to react in a positive way. You have to go in there pumped up. If you walk out of the class feeling exhausted, you've done a good job. And I've walked out of classes feeling absolutely mentally and physically sometimes exhausted, and it's a satisfying feeling because you've put your heart and soul into it. I think that's important. Empathy is another very, very big one. I know, and I can speak from first-hand experience, and I will even admit to all of you, even though I shouldn't, I failed my first course in fluid mechanics. I failed. Flat out. I didn't have a clue. Now, I could blame the lecturer, who was, by the way, lousy. I could blame a lot of things. State of mind, South Africa in 1974 was a very interesting place. There was a lot of turmoil. My first day at University of Witwatersrand in February 1973, 6 student leaders in South Africa were banned, and the first 3 days of class were an experience lesson on how to run away from the police who were throwing tear gas at us and hitting us on the head with batons. It was interesting. So, but anyway, I failed my first course in fluid mechanics. That was probably the best thing that ever happened to me. The best thing. Because it taught me, I became intrigued by fluid mechanics. So I thought, well, it's funny how we gravitate to things that maybe we're weakest at. Well, I gravitated to fluid mechanics. But it taught me an important lesson, and it taught me, I think, how to approach teaching fluid mechanics because I had failed so miserably in the first place. And I think people who are so gifted and who understand the topic so well can either be the most brilliant teacher you've ever had or can be a miserable teacher simply because they don't get it. They don't understand where you don't understand things. That connection is not made. So it can go 2 ways. More often than not, unfortunately, I think it goes the other way. People just aren't aware. They just can't understand. You don't get it. Well, folks, I failed fluid mechanics. I got it. I think I understand where people were falling down, and it helped a lot. So building up this empathy that, listen, you big shot, you failed fluid mechanics the first time through. You approach this course in a way, and when you're teaching, keep that in mind. And the empathy factor thing, I think, is very big. Respect and recognition, I think, is another important thing in establishing in a course, and that is that, and it goes and it builds on the empathy issue. That I recognize what the demands are on the lives of students, and I recognize perhaps why they're in the course, and I have to develop, a respect for what they're there for and what they're trying to do. If I want them to respect the demands that I'm placing on them and to meet the challenge that I'm setting out, then I should have this respect. And I think that's very important, that you establish this mutual respect. The best classes I've ever been in, I think I've always had that feeling that we're sitting in the classroom as a colleague where the teacher there or the professor is leading perhaps the discussion through and helping people get through there, but there's this feeling of respect rather than this terrible image that I had as an undergraduate of the professor standing there above and everybody below. It's an important one, I think. The imagery we'll talk about more. Using that, as I say, through pictures, words, stories, anecdotes, I think is incredibly important in building up or making the class interesting. It's part of the energy. It flows from the energy as well, the imagery. And then, of course, things that are obvious, I think organization and flexibility, these are obviously important to students. I don't think students appreciate being in a class that is disorganized. I don't think students appreciate in a class where they feel there's no flexibility. So the willingness to be flexible, to continually adjust within the framework of a very organized class, I think is important. And I think always strive to do that. So those are 6 basic tenets, I think, that I hold fairly important to me when developing a class, and I think they've worked by and large. Okay, let me talk then a little bit about some of the things that I think are important. So here's one that a lot of people in this class have seen. We'll talk about the concept of an image. This is one of the most famous pictures probably taken in the last 20 or 30 years. It was taken on May 18th, 1980, and this is Mount St Helens, as many people recognize when it exploded so dramatically. So it's a powerful image, and it's a powerful image for a number of reasons. First, from an emotional point of view, people look at this and they understand, and the people who lived through, who were in Western United States at that time, understand exactly the power that was contained in this explosion. So you look at this and you understand this is a powerful event, right? When you look at so that's important. The second is, from a fluid mechanical point of view, just because you understand that on an emotional level, and you look at that, and I tell you, just as an example, this is an example of a very high Reynolds number flow, you understand exactly what I'm meaning. Reynolds number then takes on a new meaning. You understand that Reynolds number, yeah, it's not just a number a dimensionless number that describes the ratio between inertial and viscous forces in a flow. Reynolds number also conveys other things, and I think this picture shows it. We talk about turbulence a lot because I teach courses on transport and mixing. This is the ultimate turbulent flow. It's got all the pieces and parts, and you like to talk about the turbulence syndrome. What exactly is a turbulent flow? Turbulence is very hard to describe or define, as many of you know. As my colleague Steve Monosmith likes to say, turbulence is like pornography, right? It's hard to define, but you know it when you see it, right? That's exactly what I think what turbulence is. So it's hard to define, but you can define it in terms of a syndrome. What do you look for when you look for a turbulent flow? Well, as you all know, the students of fluid mechanics, and there are many here, you look for this range of scales where there are lots of scales of motion. And if you look at that picture, you can see there's lots of different scales in there. There's larger sort of eddying motions, and within them smaller ones, and within those even smaller ones yet. And this picture just conveys it beautifully. And then you look in the background, and you also know about turbulent motions that they tend to decay if they're not continually energized, right? So they continue to decay. And as they decay, it's the smaller scales, for those of you who are students of fluid mechanics, you know, it's the smaller scales that decay away first, leaving the larger scales. Well, this image has that right there. Because if you look in the background on the right-hand side of that image, you can see the remnants of the cloud that came out first. There it is. It's been drifting away. You can see the large scales are left, but you can't see the fine-scale granular structure that you can see over there. So this is a beautiful image as well, because you can use it to convey that. So finding things like this, you could spend almost a whole lecture if you find the right image, and you can find things in nature that people can relate to in one way. You bring it into class and you try and relate the concept that you're trying to talk about. This is one that's worked extremely well for me, and I suspect a number of people who talk about turbulent flows. So spending time doing the kind of research in finding these images, I think, is well worth it, because they stick with you for a long, long time. I think for many people who have taken courses in turbulence, when you think about it, you think, what's the first thing that comes to mind when I think about a turbulent flow? I know, I can picture this in my head when I'm thinking about turbulence, and I can bring back all those thoughts just by picturing Mount St Helens exploding in my head, and required now to write out all the turbulence syndrome. I say, think about that picture and write about what I see in that picture, and all that comes, all the things that you like to talk about when you're describing turbulent flow, out they come. That's the kind of image I think that you need to try and create. So what would I suggest as you go out and think about careers in academia? The first thing to do is to go out and find academic heroes and heroines. I'm not talking about Nelson Mandela or Boutros Benazir. Those are heroes and heroines. I'm talking about finding academic heroes and heroines, perhaps professors that you've had before, probably, that you really think have made a difference to your life. Find them and steal from them shamelessly. I have. I'm not afraid to admit it. I think the highest form of flattery is stealing from somebody when it comes to teaching. Acknowledging it, of course, but stealing in a nice way. Teaching styles. In terms of teaching styles, you will find a number of them, and you can borrow a little bit here and you borrow a little bit there. I've done it over the years. It's wonderful. I still do. I still go see somebody who gives a great lecture, say, what can I use from there? How can I improve my own teaching? In terms of interaction with students, as I say, I learned so much by coming to Stanford University of just about how to deal with people in an academic environment. It was such a different experience for me at the University of Witwatersrand. Not that these were bad people. It was just a different way of conveying and connecting with people that I think I learned from. And so I found the people at Stanford, and I'm going to talk a little bit about some of them in the next few minutes, that I learned from, and I've tried to use their techniques. Even mannerisms and peculiarities. You'll find yourself over the years doing those things, waving your hands a lot, and I'll talk about that. So you find these people and use what they do, what you think works well. It's always good. So the first thing I would always tell someone or suggest to someone is be passionate. It comes back to the energy thing. My God, if you don't feel strongly about a topic, how do you expect anybody else out there to feel strongly about it? You've got to carry that flame and carry it forward and make it to be the most important thing, not only in your life at that time, but in the student's life as well. The passion comes out, and suddenly the whole topic just takes on a whole new meaning. The master of the war story was John Sprider. John Sprider could tell you more stories about all the great fluid mechanicians that he had met or not met in his life, and it would be wonderful. I took fluid mechanics from John Sprider 22 years ago, and it was spring 1978, and we were in the quad before they'd fixed up all the classrooms, and it was at 3:15, and we used to go till 5:05. And John was a great guy, but he wasn't exactly energetic, and at about 4:15, everybody would look at each other and go, all right, it's hot in here, it's stuffy in here. The Navier-Stokes equations just aren't doing anything for me anymore. And somebody would put up their hand and say, and he might be talking about, pitot tubes or how to measure flow or something. And you'd ask a question about it which you knew would get him started. And the next thing John Sprider would be telling you about how he, during World War II, was down at Moffett Field calibrating pitot tubes on P-47s, on Thunderbolts, and how he would be sitting on top of those big hangar structures there with a level so he could measure and watch as that P-47 came by and record the exact elevation so they could measure the air density and calibrate it and blah, blah, blah. And then he'd get going. And by 5:05, John was still telling war stories. Now, it was amazing because even though John was not the most energetic of lecturers and he wasn't the most, the subject matter we're dealing with was not that stimulating, just by bringing in that stuff made the subject come alive in a way that made such a deep impression on me. I carried it with me for many years, and I always asked the question, how could I bring this into teaching in a way that is a little less obvious than what we were doing to John there? I mean, he was stopping and telling war stories. How do you bring it into a lecture that makes it a little bit more seamless? Douglas Jardine, we'll talk about in a second. Okay, so that's something important. So passion, and to get passion into a topic often takes doing things that are not traditional. Now that leads into the next thing, which is creating the right learning environment in the classroom. This is not what you want to feel like when you're sitting in a class. I keep pointing at the screen. What a dummy I am. That's not the way you want to feel. What's he pointing at? That's not the way you want to feel when you're sitting in the classroom, right? You don't want to feel like you're sitting in a dentist's chair about to have pain inflicted on you when you're in the classroom. Now, he's sitting right there, and I have to give him credit, but Bob Street and Len Ortolano, these are my heroes in this regard. If anybody knew how to create the right learning environment, just totally relax it, make it where people wanted to get in, wanted to come to class, were excited about being in class because they knew not only were they going to learn a lot, but they were going to have fun while they were doing it. These two people, just showed me how to do it. And it was because they were very real people, and they are very real people, and they're very real about how they approach things. So what does Douglas Jardine have to do anything? This is a great saying, I think. Created an atmosphere like a dentist's waiting room. So you might as well, where does that come from? So some of you have heard this war story, so I'll tell it. So it's not so seamless, but it should be anyway. So it goes back to cricket, and it goes back, and Steve Armfield will know all about this. Back in the early 1930s, Australia had a wonderful cricket team, and they went to England and just beat the pants off England. Absolutely humiliated them. And they carried back, which was then the equivalent of the axe, which is called the Ashes. And the Ashes is this silly little pot, brown urn about that high, that has in it the remains of a cricket bat that was burnt. They burnt this cricket bat and put the ashes into the cricket bat, and that, Johanna knows about it too, and that represents, if you won the Ashes, then that was the most important thing you could do. It was like winning the big game. You could lose any other game, but win the Ashes, and then national pride is restored. So England went to Australia in the early 1930s, kicked their butts. And so now, on the way over, a few years later, to Australia, the then English cricket captain, Douglas Jardine, he was charged. The whole nation's eyes were upon the English cricket team that was sailing towards Australia to go and regain the Ashes, right? And Douglas Jardine figured, well, how was he going to negate the strength of the Australian cricket team, which was then the incredible batting? How was he going to do it? What he was going to do is he was going to take the strength of the English team, which were two fast bowlers, one named Harold Larwood and the one named Bill Vose, and he directed them, he said, don't bowl the ball essentially at the strike zone, which in cricket is the wickets, the three things that stand up. He directed them to bowl the ball in such a way that the batsmen were more concerned about the ball hitting them than about them hitting the ball. It was called body line bowling. So needless to say, these guys, they could bowl fast. They could bring the ball at 90, 95 miles an hour. And what they do is, you pitch the ball into the ground and it would kick up at a terrible angle and come right at your body. And the last thing you were trying to do, the last thing in your mind was, where shall I dispatch this ball and score some runs? The only thing in your mind was, how do I stop this ball from hitting me? Because it's going to kill me if it does. And so they'd have this whole ring of fielders around, and the ball would become flying somewhere around here. And you'd be doing this to try and stop it from hitting you, and they'd just be waiting and catch the ball. Well, the Australians, of course, were furious. This simply was not cricket. So Ray Robinson, this is a long war story, isn't it? Ray Robinson, who was then a famous cricket writer, and I really enjoyed when I was a kid reading about cricket and war stories. Ray Robinson was writing this book about this series, which is known as the Bodyline series forevermore. And he had these little pictures of players, Don Bradman and Stan McCabe and Harold Larwood and Bill Vose, and there'd be a little line underneath each one. Don Bradman, greatest batsman that ever lived. And there's a picture of Douglas Jardine, and right underneath it, created an atmosphere like a dentist's waiting room. It was amazing because it carried to me, imagine what it was like being at the Sydney Cricket Ground at that time when these guys were bowling. The crowd was ready to tear the English team apart. They were ready to kill Harold Larwood. Poor Harold Larwood had to have bodyguards because everybody took it out on him. Imagine what that atmosphere was like. It was an atmosphere like a dentist's waiting room. You know what happens in a dentist's waiting room. Nobody talks to each other. Everybody looks around because you know you're going to go next door and you're going to have all this pain inflicted on you. Don't ever create an atmosphere like that, because no learning will occur if you do. All right. Don't read the bottom yet. Do not be afraid to make a fool of yourself to create the internal image. I mean it. And this is, I got to give Bill Reynolds. Bill Reynolds is just retired, a wonderful professor. He would get up there, and you knew Bill Reynolds was into it, and the passion and energy was going. When the glasses would start sliding down the nose, the voice would go a couple of octaves higher, the arms would start flailing around. He'd get this little giggle in his voice. And how can you resist passion like that when learning about something? You just wanted to go out and do it afterwards. He knew how to do it. And he would think nothing. He would think nothing of giving you his own personal demonstration of what the flow is doing. And he'd stand there doing this, demonstrating how fluid is pumped between hairpin vortices and the boundary layer. And doing all these things, and everybody thought, oh, the guy's National Academy of Engineering, distinguished professor, standing there making a fool of himself, and I can still see him do it, and I can still exactly remember the words. That image lived with me forever. It's a good one. So I tried that a few years later, and I don't normally do this, folks, and I apologize for this if it sounds like it's self-promoting, but I had to show it because it was recognized in the Tau Beta Pi survey by a student. Now, I'd done this in a transport and mixing class, and so you'll be able to understand what I did, but it reads, superbly done, stunningly original, Koseff acting out the motions of a blob of pollutant in his finest role. the Hicksville Times. Apparently, I'd stood there acting out what happens to a blob when it gets in a turbulent flow. And this is when I was much younger and I was able, I had the athleticism to do it. I wouldn't dare do it now. But it's a powerful technique. The other thing is seize the moment, and this I give credit to Steve Monosmith. So Steve was driving by on campus, a few weeks ago, and apparently a fire hydrant had blown its top. And there's this wonderful jet of water, kind of looks like Mount St Helens, but it's water, blowing out of there. So he goes and runs to the environmental fluid mechanics lab. He's not like Linda, who walks around with a camera all the time. And he gets the digital camera and he takes some pictures. Well, I can tell you something now. This picture showed up in a midterm exam 1 week later, used in the most creative way. Because you can estimate, just from the height of the fluid, what the velocity coming out is and what the flow rate is. And Steve had them do that. He wanted to know how much water was being wasted. And they could, just from that picture, you could and applying fluid mechanics, you can do that. It's just a fabulous example of seizing the moment and then using it in a very constructive way in a class. This, by the way, is the result. This is where the water's going. And for those of you who know a little bit about fluid mechanics, you can see there's a supercritical flow right there. So we talk about supercritical flow and hydraulic jumps, and there's a nice angular hydraulic jump. So these things don't just occur in the lab, they do actually occur in nature as well, and even in your parking lot. Everybody knows about hydraulic jumps. If you go whitewater rafting, you know about them. A few years back, we did that on the Upper Klamath River. We went whitewater rafting on a Class 4 Plus. I don't know if you've ever done this. But it's a fluid mechanics dream. It's a fluid mechanician's dream. Because here you are going down the river, and suddenly you come to this rapid, and where did the sky go? Because in front of you sitting is this huge wall of water. Something like that. So imagine, to put it in scale, you're an ant on a leaf going down there, and now you've got to get over that thing right there. Well, it's the same kind of thing when you're whitewater rafting. Different scale, same phenomena. You can demonstrate it. You can relate to someone's personal experience. All that comes together in a very, very positive way. All right. So those are the kinds of things that I wanted to talk about there. Whoops. Let's go. Now let's go to this multimedia fluid mechanics. So here you are as a fluid mechanician, and you're about to teach, and you look at all the tools around you. You've got your textbook, right? You've got Milton Van Dyke's book, Gallery of Fluid Motion, all these beautiful pictures that have been collected over the years. You've got that, because that's how you can do your images. You've got the National Science Foundation sponsored series on movies made circa 1960s, 1965, 16 millimeter, fortunately converted to video over the last few years. You've got that. So you've got your videos over here, you've got your book over here, you've got your gallery of fluid motion over here. What else? You've got your lecture, and then you've got your war stories. And they're all in different places, and they're all in different places. And then you've got your laboratory, where you desperately want to be in the middle of a lecture because you want to demonstrate this wonderful phenomenon, or you want to take people outside and say, look at all that water running down the drain, but there's an angular jump. That's what I'm talking about. How on earth can you pull that all together in one place, at one time, and allow a student to experience it? Well, we couldn't up to now, until Bud Homsey wrote this wonderful proposal to the National Science Foundation, where he said, I want to develop this multimedia module for teaching fluid mechanics. And we had lunch one day, and I told Bud, before he brought this up, I said, I was listening to Charles Kearns and Barbara Jean Maliska one time talking about some projects they'd done for the art department where they'd used technology to catalog all this art, and you could just call it up at any time, and a faculty member teaching a course in art could just go to the computer, find that image, put it up. And I started thinking about, wow, that would be great if we could do that with fluid mechanics, and we can get all these stories in about these great fluid mechanicians and what was Bernoulli's life like, and how many children did Couette have, and yeah, he had the same problems that you and I did, you know, getting up in the morning, yet he did all this stuff. How can you just bring that all together? And we started having this discussion, and he told me about this project, and I said, well, I'd like to participate. And he said, good, because I was about to ask you to, so it was good. And so this is the end product. This is about to, I'm just going to show you a few parts of it because I want to leave time for some questions if there is any. But this is sort of an attempt, a first attempt to try and pull all those things together. So for those of you who are not fluid mechanicians, I apologize, but I think you'll enjoy it anyway because you'll get to understand what we're trying to do here. So I've got a few things to show. First thing is, you know, you talk about theory, you talk about experiment. You've got the experiments going in the lab. You can do the theory on the board. You can show pictures and all that, but it's not all together. How do you pull that all together in one go? So let's. This will take a few. Some of these things take a little bit of time to get going, so you'll have to bear with me. But if anybody has any good jokes to tell while we're loading this up, feel free. I'll tell you this. Don't try this at home. This is not something you should do in your spare time. We thought, you know, we all thought, HTML, Java, blah, 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 you know, read a few books, I'll do all this stuff. This took, you know, professionals, you know, working flat out, a whole team, just to get this kind of stuff together, and it's tough to do. There's a lot of stuff here. So what do? I go to Special Features, and then I go to Galleries, Charts, and Graphs. Then I go to Comparison of whoop. Okay. So here's a good example of what we're talking about. So let's see what comes up here. Hopefully it'll come up. And what are we going to see, here we are, is something that's extremely nice. What we've got here is flow going past an obstacle. So imagine, for those of you who are not fluid mechanicians, you've got some flow coming down there, and you put over this table, you put an obstacle in the middle of that table. What's going to happen to the flow around that obstacle? That's essentially, okay? So there's something called, I wonder if the light is a little hard, it makes it a little hard to see. There's something called potential flow theory. That's the theory. And the theory will predict what the flow looks around the obstacle. So I can choose a cylinder. There's a cylinder. I can choose an ellipse. I can put a block in there. I can do any of those, and it's all computed, and it's right there, and the student can look at that, right? Very nice. So you say, all right, what if I did an experiment, a potential flow experiment? Well, for those of you who study fluid mechanics, you all know that there's a famous fluid mechanician named Healy Shaw. Healy Shaw invented this Healy Shaw device, which is a flow through a very, very thin environment, a very, very narrow environment, where essentially you can create potential flow. So if Healy Shaw did this experiment, which the theory predicts like this, how would it look? So you can click on that. Come on, baby. And we start up the movie, and there it goes. So now right there, you didn't have to go to the lab, you got it right there, you can wander, and wow, it looks pretty good. It looks very close to the experiment. So this potential flow experiment, which is done at a very, very low Reynolds number, looks very, very similar to the theory. You've got it right there. And as you can see on the screen, I can just toggle back and forth between potential flow theory and potential flow experiment. Okay, I could just go back there, and I have it right there, and the experiment right there. Very nice. Okay. Now you might answer, well, what happens if I don't do it in a low Reynolds number, Healy Shaw environment, just to enrich it? What happens if I have a fairly high Reynolds number? So I don't satisfy the same assumptions. And there's a movie right in there of the flow behind it. You know, you can see. So this is what the flow would look like, folks. You know, you ever wondered why when you're standing, you know, behind a building, you're standing there and suddenly your hat goes whoosh, you know? Well, you're standing there in the flow. It's because that's you standing there, and there's the wind, and you're standing there, and this flow is flapping back and forth, and occasionally you get a big gust that knocks your head off. So you've all experienced that because you've stood in the lee of buildings while this stuff was going on. All right, well, that's fine. So now you might ask, well, what do we know about this fellow Healy Shaw? This is great. Let me see if I can find out. You want to see, is there anything, what's the dirt on Healy Shaw? Should I know anything about Healy Shaw? So you go to the history module, and you go find Healy Shaw. So this is where it sort of comes together nicely. Takes a little, if we could speed it up a little, it would obviously be ideal. But there's Healy Shaw, that's what he looked like. I was lectured to by people who looked like that. And then you go to contributions, and you can read about his life. He was born in Essex. You go to contributions, and then you start reading through this thing that we did on contributions, and you find something, yeah, you know, blah, blah, blah. Here's something interesting for. I'll read it. A controversy surrounding the publication, a publication he'd done, arose when one of the leading scientists of the time, Osborne Reynolds, who a lot of you know, published an open letter claiming that Healy Shaw's interpretation was incorrect, and furthermore, he claimed that the method that Healy Shaw was using was taken from copies and references to publications bearing on the subject communicated to Healy Shaw. So basically, here's Reynolds accusing Healy Shaw of plagiarism. Huh? Well, you know, it's kind of hard to get that. This is good because it starts telling you about Healy Shaw and Reynolds, and they had this big conflict. And Healy Shaw demanded that, you know, an apology, and Reynolds said, well, kind of, you know, I apologize, but I still think you plagiarized, kind of thing, and that's where they left it. But this, you know, brings in an element to the whole problem that I think is important. Because I know for myself, when I started out, and I first read, like the best paper, you read this paper in the Journal of Fluid Mechanics, right? And maybe it was written by Healy Shaw. And this paper is laid out in the most logical, beautiful fashion, a natural progression, so one would think, of thought and experiment and conclusion and this, that, and the other, and everything's laid out there very, very carefully. It doesn't begin to tell the story of what went on. It doesn't begin to tell the story. That paper might have been held up for 2 or 3 years because there was this raging controversy that went on between Healy, Shaw, and Reynolds over this topic. It gives you a little bit of pause when you start reading about some of the conflicts that these people went through, that, hey, they're just like you and I. They struggled for 3 or 4 years. That paper that came out doesn't even begin to reflect all the hours and the trials and the tribulations that you went through to produce that result. It adds an element of humanism, if you want, to the topic that is simply not there when you read the paper, and it makes you less intimidated because it realizes, yes, you can do this too. These people were just the same as you. They had the same problems as you are. Knowing something about their personal lives and what motivated them, I think, is extremely important because it just takes away that element. There's lots of other things that I can show here, but time is moving on, so I think I'll stop there, and I'll be happy to take any questions if you have them. Thank you very much.
Questions?
You got any images of a clam out in the middle of that?
No. Got a butterflies flying. I can show you other images if you want to see them. You want to see other things that we have on here?
I wanted to see the airfoil, actually.
The airfoil?
With the high Reynolds.
The airfoil with a high Reynolds number. Well, I'll show you something else. How many people have been to breakfast with someone who plays with their food? You all have, right? You've all been to breakfast with someone who plays with their food. I am one of those people. I play with my food because I think there's great fluid mechanics in food. So let me show you an example of that. So this is one where you, let's bring it up. I like to drink coffee, just like everybody here, and I like to drink latte, right? And I hate it when somebody brings me a latte and it's already mixed together. Thank you, Rachel. That tends to happen a lot at Starbucks. I want my latte to come with, you know, the milk at the bottom and the coffee and above, because I got a lot of fluid mechanics to do with that thing. So, yeah, a lot of us thought about that, and we said, yep, Stirring cream into coffee. That's a real cool experiment. You know, that teaches us a lot about fluid mechanics. So here we have, you can stir your cream in a virtual way into your coffee. So here's a movie. All right, so here it goes. There's the coffee. We have a little exercise in a class I teach where people are invited to do this. All right, so there comes the cream. In it goes. Of course, we all know the cream is cold and it's a lot more dense and heavier, so it sort of sloshes around at the bottom. Here comes the big mean spoon, so I'll stop it just before the spoon gets in there. But you can see I poured it in, and there was initially those nice turbulent motions that you recognized from looking at the picture of Mount St Helens, right? But suddenly they started dying out, and they started dying out because there's a density difference which exerts a force which starts squeezing that and squeezing out the motion. So if I let that just damp out, it'll slosh around there for a while, and eventually it'll settle as a nice layer at the bottom. Unless, of course, you do something to that. You induce some energy in there. You stir the fluid by straining it with the teaspoon, and lo and behold, you mix it out real quick. You can do wonderful things with that in teaching. It's just a real experience that everybody's been through. You can invoke that image, and you can make a lot of progress with that one. Yeah, Drew. I think that's a great question. And that's the struggle, I think, that we all find, especially when you're teaching a first course in anything, is how do you, and you know, what you have to do is essentially project yourself back, 20 years back to when you were there and you were facing this for the first time. And the better you are able to do that, I think the better you are able to create a lecture and deal with the issue that is facing them. That's the challenge. It's not an easy thing to do. I think you have to continually think about how you teach. I think you have to continue to think about the jargon that you use. And when you're preparing the lecture and you're looking at it and you say, am I using concepts here or talking about things that they're not comfortable with, throw them out and try and simplify to the point where you're only using jargon or technical jargon that people have experienced before. But the other thing is the image then. You just got to keep relating it back as much as you can to somebody's experience. And more often than not, the things that we're going to be talking about, people have seen or experienced. And if you can do that, if you can make that connection, I think it's really important. I remember, you know, going into class the first time, we were talking about linear and angular momentum, and I got hold of someone's skateboard, and I actually really made a fool of myself because I was trying to demonstrate what happens, you know, when you've got momentum in one direction, then you get hit on the side, you know, and everybody's been on their skateboard and got hit by someone else, and you figure out which way you're going to be going. Well, those things, you know, they're good. They also break the ice in the class. Images can be very powerful. I remember when I taught basic fluid mechanics, and this was a big class, 45, 50 people. Half the students were undergraduate civil engineers who needed to be there. A lot of them didn't want to be there. There was a good chunk of students, graduate students in the construction program, who had to be there because they were told they needed to take this course. Then we had chemical engineering undergraduates had to be there. We had this whole mix of students who didn't know each other, and on the first day of class, it was like a dentist's waiting room. Not because of anything I was doing, of course, because nobody wanted to be there. So how are we going to break this, you know? Now, Lynn Orr gave a talk a few weeks ago, and months ago maybe, and he talked about surface tension and bubbles, and he gave a demonstration. But I remember, all right, I got to do something. And we were talking about surface tension at the time. So I was up at the Exploratorium, which is a great place, and I got this big bubbles thing. I don't know if you've ever got these. How to make the world's biggest bubble, right? And you get Joy liquid, 3 parts this, you add glycerin, and you do everything. And I brought this big bucket of stuff into class with this big bubble maker. And I remember everyone was sitting around, and I dipped it in, and I opened it out, and I went over the class, right? Walked from the front to the back, and I had this gigantic bubble. Imagine this big bubble sitting in the middle of the room, right? And there it was, kind of doing this, kind of like a sea lion doing the Macarena. It was sort of, and everybody was looking up at it, you know, going, oh my God. And the next thing it popped, and this big goober of stuff fell right on Sharon Jones' hand, and she went, ew, yuck! And everybody was just like talking about it, and from that moment onwards, the tension in the class had been broken as the bubble. It was great, and the class just took on a whole different thing. So there was a good example And people, you know, Sharon Jones, when I see her today, I still remember that big bubble that you burst over my head. So it was pretty cool. I think that's an excellent point. I think what you want to do is inspire, but you don't want to substitute. Making the leap between taking words and equations and translating them into physical phenomena is as difficult as taking the physical phenomena that you've got in front of you and saying, write the mathematical or the physical equations that describe it. Going back and forth either way, I think, is an important, very important thing to do, in both directions. And I think, you know, the more experience you have at doing it and the more opportunities you have to do it, I think you'll find your own comfort level in terms of what you want to do. But you're an engineer, and you're going to be paid to give engineering answers, which are going to be, you know, it's not going to solve anyone's problem if you draw a picture for them and say, here's your solution. You know, well, how am I going to implement that? You know, but in terms of helping people understand why your solution is important or why you think it's the right solution, being able to create those images, I think, is important. You know, you talk to people who go to Congress and testify. You know, they talk about making the 30-second, you know, soundbite. You know, sort of taking something and making the analogy. That's what's going to get through. Going to testify, you know, at the state about the problems in the Delta, or going down to Palo Alto and talking about problems, you know, if you just talk technical jargon, mathematics, they're not going to understand it. Creating an image that they can understand by interpreting your deeper understanding of it, I think will ultimately get people to where you want them to be. I think that's sort of the interplay that I was trying to talk about.
Jeff, thanks
Yeah.
very much.
Yeah.